So if you've been following the playlist so far, then you may know that we're in the integration topic, and you know at the start that we can anti-differentiate something to get its, original functions, and we can use this kind of notation. And then for some reason, we start talking about left endpoint. So left endpoint, I don't know if you're doing that, and right endpoint, rectangular approximation. And you might be thinking, what is the link between these two? Is there any at all? Why are we talking about both of these? Well, it turns out that if you want to find the area underneath, now we know that from before, we can use geometry to actually find out the area between two x values. So let's say you got x is equal to a to x is equal to b, and if you want to find the area that's underneath the green curve, you can draw some rectangles. So maybe we'll start off by drawing a few. Actually, you know what? Let's use the left endpoint approximation. What we're going to do over here is we're going to draw two rectangles. Okay. Over here you can see that while I can kind of estimate the area underneath, but it's pretty clear that there's this area over here that's not accounted for, and this indicates there's an underestimation. So what gives over here? How can we make sure that we get the exact area underneath, or something very close? Well, we can do that if we, let's say we double the number of rectangles we use this time. So instead of using two rectangles, I'm going to say that I want 4 rectangles. So in this case over here, draw one over here, another one here, my third one, and my fourth one. And of course, these are all equally spaced. So you can definitely see that in this second case over here, where the number of rectangles is equal to 4, it's much, much better. So n is equal to 4. It's better than where we have only 2 rectangles. Okay, but let's try to figure out a very general case of what's happening here. It means that if I was to double the number of rectangles again, if I have 8 rectangles, what does this mean? Is this a better approximation? Well, it definitely is. We can see over here visually that the more rectangles we use, the better. Okay, so here's what we're going to do. Let's figure out a very general expression to figure out the area of one rectangle. The area of one rectangle is going to be, it's going to be the width of whatever rectangle you use. We're going to call this delta x. And what is the height over here of one rectangle? Suppose we're using left end approximation. So over here, this height over here is going to be f of x. I'm going to say xi because over here, this I here just stands for what number of rectangle are we using. So for example, over here, this is going to be x1, comma f of x1. And in the second rectangle, so going back to the blue rectangle case, I'm going to say this is x2, comma f of x2. Okay, so if we want to find the area of one rectangle, then this is going to be f of xi multiplied by delta x. And this doesn't change for whatever rectangle you use. So this one over here is the same for each rectangle. Okay, and of course, this is the area of rectangle I. So for rectangle 1, where I is equal to 1, you find the area of the first rectangle. So you need f of x1 over here. But what we want is not the area of one rectangle, we want the area of all of them together. And what you can use over here is, instead of saying the area of rectangle I, we can say that we want to sum up all of these rectangles. So when you find the area, this is, let's rewrite this. So the sum of all rectangles is going to be the summation of the area of all rectangles. So this part over here, so this, which color should I use? Here, this is the area, and this summation sign, I'm gonna need more space. Scroll down. The summation. So summation just, well, in layman's terms, would say that it's the combined sum of all rectangles from our first rectangle, so this is where I is equal to 1, and to n. But what about this n over here? Well, this n, we want this n to be as large as possible. So instead of saying, well, instead of this one being 4 or even 8, how about we make it an extremely large number? And for that, we're going to say the area is actually the limit of n approaching infinity. So we want this value up here to be as large as possible, and we're going to start from our first rectangle. So what this is saying here is we want to start from our first rectangle and going all the way to our infinite number of rectangles. We want to find the sum of all these rectangles that are put together. And what integration does for us is it sums all this information up very nicely for us, because what happens here is that this part will turn into the integral between x is equal to a to x is equal to b. This integral sign really means I want an infinite number of rectangles, and this part over here, another color, is just saying that I want the integral of all the rectangles underneath the curve f of x multiplied by dx. And you can think of this as, well, the first principles of differentiation, if you like, kind of like how you do first principles of diff from the previous topic. But in this case over here, this is really what kind of role rectangular approximation plays in integration, and why we need to use it for calculating the area under the curve. And it works out quite nicely.